A key tool in solving diagnostic problems in hematology is understanding bilirubin metabolism and the clinical tests that are used to assess it. It starts when discerning macrophages in the reticuloendothelial system remove and phagocytose senescent or otherwise abnormal red cells from the circulation. A major effort is put into salvaging as much of the reusable parts of hemoglobin as possible. Globin is broken down into amino acids. The heme ring is opened, allowing the release and reuse of its iron. Heme oxygenase acts to produce the green pigment biliverdin, which is reduced by biliverdin reductase to the yellow pigment bilirubin. Bilirubin is lipid-soluble and can cross the macrophage membrane, making it into the plasma, where it complexes with albumin to keep it soluble and confined in this aqueous environment. In the laboratory, this is referred to as indirect bilirubin and is normally found in low levels, typically less than 1 milligram per deciliter. The bilirubin is transported into the hepatocyte, where it is conjugated and thereby made water-soluble by UDP glucuronal transferase. Conjugated bilirubin is transported into the bile canalicular system, eventually making its way into the gallbladder. Under normal circumstances, a small amount of water-soluble conjugated bilirubin is released into the plasma. In the laboratory, this is referred to as direct or conjugated bilirubin and is normally found in levels well below half a milligram per deciliter. If the plasma levels rise abnormally, bilirubin may become detectable in the urine. Conjugated bilirubin in the gallbladder is emptied into the intestine, where bacteria convert it to urobilinogen, which is eventually oxidized and eliminated in the stool. A small amount of urobilinogen leaches into the blood and is normally detectable in the urine. In the laboratory, this is usually measured as urine urobilinogen. Under some circumstances, red cells lyse and release hemoglobin right into the plasma, a condition called intravascular hemolysis. In the plasma, the hemoglobin tetramer dissociates into dimer. The dimer immediately binds to a plasma protein called haptoglobin, which transports it to the macrophage so the salvage process can be implemented. In the laboratory, plasma haptoglobin can be measured and normally falls within a wide normal range of tens to hundreds of milligrams per deciliter. When a lot of hemoglobin is liberated into the plasma, haptoglobin can essentially get used up, with levels falling to zero. Plasma hemoglobin can also be measured in the laboratory. Normally it is undetectable, and the plasma has a clear, light yellow color. If there is a lot of intravascular hemolysis, the plasma can become pink or red. The renal threshold can become exceeded, and hemoglobin dimer may be found in the urine and turn it pink or red. So the common routine laboratory tests that are used to assess bilirubin metabolism are plasma indirect bilirubin, normally low, but elevated when there is a lot of hemoglobin to salvage, as in a hemolytic anemia. Even when it is elevated, though, it never makes it into the urine because it is not water-soluble. Plasma direct or conjugated bilirubin is normally low, but becomes elevated when the hepatocyte or biliary tree is not functioning properly. Because it is water-soluble, it can be detected in the urine and be measured on a routine urine dipstick test. Urine urobilinogen can also be detected using a urine dipstick test. When it is elevated, it may indicate either liver damage or very high bilirubin processing, as seen in hemolysis. When there is no detectable urobilinogen in the urine, it may indicate severe biliary obstruction. Plasma hemoglobin and urine hemoglobin are generally not detectable unless there is intravascular hemolysis. And plasma haptoglobin levels can decline all the way to zero, depending on the degree of hemolysis.